Okay, a simple example of a probability distribution would be, let's say I ask you to construct a probability distribution for the number of girls in a family of 3 children. We've talked about this a lot. I came from a family of 3 children. Me too. Well, almost. But anyway. Okay. So that's what I want to do. So when I say a probability distribution, first of all, the bottom line is what we call a random variable. And so the random variable is a variable whose outcomes are determined by chance. It is a quantitative variable. So in this case, our random variable is going to be the number of girls in a family of 3 children. The probability distribution lists all of the possible values and the probabilities associated with each one. So if we've got 3 children and we're interested in the number of girls, what are the possible values for that? 0, 1, 2, and 3. Okay, those are the possible values. And then we can use various techniques to come up with the probabilities associated with each of those. But for now, we'll just use, oh, this is beautiful. We're going to use our tree diagram or our sample space, which we looked at a good bit in the last chapter. Looked like this. Okay, so all right, if we wanted to calculate the probability of 0 girls, it's going to be what? One-eighth. Very good. If we want to calculate the probability of exactly 1 girl, we get 1 girl here, here, and here, so it's 3/8, right? Probability of exactly 2 girls, 2, 2, 2, so that's also 3/8. And then the probability of 3 girls is 1/8. Okay, so this is a very basic probability distribution. List probabilities, or rather the possible values, 0 through 3, and the probabilities associated with each one. Okay, in order for a probability distribution to be a valid probability distribution, we have to have 2 additional things. Each of the probabilities needs to be between 0 and 1, and the sum has to be equal to 1, or approximately 1 if we've converted to decimal and rounded. Okay, so this is a probability distribution. All right, and so in that second section, we talk about probability distributions in general, and then from there we start to talk about probability distributions in particular. There are many different types of probability distributions. In this chapter today, we're going to focus on the binomial probability distribution. In the next chapter, we're going to focus on the normal probability distribution, and we're going to get comfortable with both of those. Okay, so as far as the binomial distribution, there are 4 requirements. First of all, when we identify a binomial probability distribution, we have a fixed number of trials, and I'll explain what all of these mean. Okay. But basically, the probabilities apply to a certain number of trials when we've repeated an experiment a fixed number of times. Okay, then we have 2 outcomes. And we generally call these outcomes success and failure. Okay? And success doesn't have to be a good thing. It's just the thing that we're interested in. Okay? So we've got two outcomes. That's where the bi comes from, binomial. We've got two outcomes. We classify them as success and failure. And sometimes we can have more than two outcomes, but we can always break our experiment up into two outcomes. You're either the characteristic of interest or you're something else. Okay? Even if something else has several different things in it. Okay, also we have the probability of success. Is the same for each trial. And finally, the trials are independent. Okay, these are the four characteristics of a binomial probability distribution. If ever you needed to be able to recite something, this is it. Not that I would ask you to do that, but when we see the problems, they're not going to say, I'm a binomial distribution. That's going to be what you have to determine, and you've got to ask yourself these four questions. Okay, so if we think about the experiment that we had a second ago with our family of 3 children, we were interested in getting 2 girls. Does that meet the requirements of a binomial distribution? Did we have a fixed number of trials? Yes. What we were talking about only was in reference to a family of 3 children. Okay. Did we have 2 outcomes? Yes. Okay. Boy or girl. And in our case, the success was a girl because that's what we were interested in. Okay. Probability of success is the same for each trial. Yes. Right. Probability of getting a girl remains the same from trial to trial. Okay, and are the trials independent? Yes. Okay, what happens? The gender of the first child does not determine or affect the probability of the next child being a boy or a girl. So it met all of the requirements of a binomial experiment. Okay, and we'll do that again with some other examples, but let's look at some of the notation regarding the binomial experiment. Okay, S and F, that represents our success and failure. Okay, when we talk about the probability of success, we use that lowercase p. Okay, probability of success. Okay, is denoted by lowercase p. Probability of failure, some textbooks would use a Q. That's what I prefer to use. I think in this textbook, he actually says, who wants to take a guess of what the probability of failure might be? If a success, okay, the total is what? 1 minus p. Okay, so probability of failure is 1 minus p. Okay, all right, if success has probability of p, probability of failure, 1 minus p. Okay, N is going to be that fixed number of trials that we talked about. And X is going to be the exact number of successes that we're interested in. Okay, we already said lowercase p represents the probability of success. Lowercase q represents the probability of failure. And then probability of X is the probability of exactly X successes. Okay. All right. So let's take a look at this example. Did everybody have that? Okay. That's right. Okay. I don't think so. Except, lowercase p would maybe make you think of probability. Okay. All right. It says consider an experiment in which five offspring peas are generated from two parents, each having the green-yellow combination of genes for pod color. Recall from the chapter problem that the probability that an offspring will have a green pod is 3/4 or 0.75. That is, probability of green pod equals 0.75. Suppose we want to find the probability that exactly 3 of the 5 offspring peas have a green pod. Does this procedure result in a binomial distribution? Let's start there. Okay, so first of all, if it's going to be binomial, we're going to have a fixed number of trials. Do we have that? Yes, this is in reference to 5 of the pods. Okay, do we have 2 outcomes? Yes, green or yellow. Okay, is the probability of success the same for each trial? Yes, the probability of getting a green pod is what? 0.75. Okay, and that comes from the tree diagram, which maybe we'll look at that a little bit later, but they already gave us 0.75. And then finally, are the trials independent? Yes. Okay, they're all independent. So this meets all 4 requirements of the binomial distribution. Okay, the second part is if this procedure does result in a binomial distribution, we want to identify the values n, x, p, and q. Okay, so n for us is what? 5. We got 5 trials. X is 3. We're interested right now in 3 successes. Okay, P is the probability of success, so that's 0.75. Okay, and then Q would be what? 0.25. Very good. Okay, Q is 0.25. Notice that Q is usually not given to us in the problem. We need to figure that out. It's 1 minus P. Okay? All right, is there a part C to this one or no? Okay, good. All right, let's look at another. Determine whether or not the given procedure results in a binomial distribution. For those that are not binomial, identify at least one requirement that is not satisfied. Okay, so here we have treating 863 subjects with Lipitor and asking each subject, how does your head feel? Is it binomial or not binomial? Okay, not binomial. Why is that? Okay, all right, we got more than 2 outcomes. All right, that'd be the first thing I would think of, is there more than 2 outcomes. All right. Okay, B, treating 152 couples with the Y-sort gender selection method developed by the Genetics and IVF Institute and recording the gender of each of the 152 babies that are born. Is that binomial or not binomial? Okay, all right, let's see if it's binomial. We've got a what? Fixed number of trials, 152. Probability of success is the same from trial to trial. Trials are independent, and we've got 2 outcomes, boy or girl. So I would say yes, this is binomial. 15 different governors are randomly selected from 50 governors currently in office and the sex of each governor is recorded. Okay, would we say that's binomial? Okay, again, yes, we got a fixed number of trials. Is this binomial? We got a fixed number of trials. We got two outcomes. It's a relatively small sample space. So I'm kind of questioning independence and also whether or not the probability of success remains the same for each trial. Our state, we have a woman who is governor. Let's say she's sampled, she's taken out, we toss her out, right? She's not in there. So, so the probability of selecting another woman, the next woman changes, right? Because we've got to. So I would say this is not binomial, okay? Because the probabilities are not the same from trial to trial. I still, if it's something about the way that we're sampling. If we're sampling and not replacing, then that makes those samples dependent. Okay, versus when we looked at the example with the peas, they just gave us the 75%. And so each time we get ready to watch a new pea generate, there's a 75% chance that it's green versus 25% that it's yellow. Okay? Yes. Why is it not binomial? I said because the trials are not independent and the probability of success is not the same from trial to trial. Okay? That's why I would say this is not binomial. Okay? What's important right now is that we kind of think about the idea of what it means to be binomial. I'm not going to give you one that.
What was the second thing you said about they're not independent?
And the probability of success was not the same for each trial. Okay? If I take a person out, then the probability that the next person is going to be female. Who's into politics? Which other state has a female governor? Okay. Well, anyway, if there's another, it changes. So the probability is not the same. Okay, from trial to trial. That's what's important. Okay. 200 stats students are randomly selected, and each is asked if he or she owns a TI-84 plus calculator. Is that binomial? Do we have a fixed number of trials? Yes. Probability of success, is it the same from trial to trial? We got a larger sample here, 200. We could probably, as a college, figure out what percentage of our students, our 11,000 students, have the calculator. So at that rate, we'd say yes, the same from trial to trial. The trials are independent. Whether or not you have it shouldn't depend on if the next randomly selected person has it. And what else? Independent. Okay. All right. So we're going to say that one's binomial as well. All right. And we'll talk some more about the idea. Then you'd be 1 minus p in that other probability. Okay. All right. There was a special note concerning independence for a binomial distribution, but I don't know what that is right now. So we'll come back to that a little bit later. Okay. Now, because we hadn't calculated any probabilities yet. So it says a Gallup poll of 12,000 or 1,236 adults showed that 12% of the respondents believed that it is bad luck to walk under a ladder. Okay, consider the probability that among 30 randomly selected people from the 1,236 who were polled, there are at least 2 who have that belief. Given that the subjects surveyed were selected without replacement, the events are not independent, can the probability be found by using... Okay, this has something to do with that last thing, so let's not talk about that right now either. Okay. The author got a little too deep. Okay. Here comes our... Before I tell you the formula for binomial, I'm going to try to help you understand it. This is where things get a little scary, but that's okay. Let's go back to our example with the number of girls born in a family of 3 children. Okay, and we had 1/8, 3/8, 3/8, and 1/8. Okay. How, besides drawing out the sample space, because this was just a few children, if we had a lot of children and we wanted to do something like this, how would we be able to come up with these probabilities? Well, let's consider this one, where we've got 2 girls. Okay. The outcomes look like we're interested in the probability of 2 girls. So we're considering the outcome of girl, girl, boy, or girl, boy, girl, or boy, girl, girl. Right? Those are the possible ways. Those are the simple events that we would have to consider. Either way, in each of these we get how many girls? 2 girls and 1 boy. We've got 2 successes. We've got 1 failure. So, not that boys are failures, but in this case, it would be a failure. So, basically, whatever the probability of success is for this, we're going to raise that for each of these to the 2nd power. Right? Because there are 2 successes. And we would multiply this by the probability of failure raised to the number of failures, which in this case is 1. Okay? So, by the time I did that, it doesn't matter which order these things are in. It all comes out to probability of 2 successes times the probability of 1 failure. So how do I count up how many successes we have? Well, curiously, that comes from something like 3 choose 2. Okay, if we do 3 choose 2 on the calculator, then it actually comes out, I think, to 3. Somebody check that out to make sure. Okay, but how do we turn this into some type of a formula? Okay, the formula for, okay, good. Okay, the probability for X successes, okay, is, in this case, well, let's back up for a second. N for us is what? Three, right? We're looking at 3 trials, so N is 3. Right now, we're interested in X being what? 2. Okay, and then I'm not going to put the P's and Q's in right now. The formula looks like N choose X, right? We had 3 choose X. We take the probability of success and we raise it to the number of successes, right? We had here, if P is our probability of success, we raised it to 2 girls. Yes? Okay? Times the probability of failure raised to the number of what? Failures, which we could express by saying N minus X. This is the formula for binomial probability. Okay? You can think about that tonight as you're going to sleep. When you want to know, like, where did that formula come from? Oh, yes. Yes. I'll show you how. Probability of X equals N choose X, P raised to the X, and Q raised to the N minus X, where N is the number of trials, okay, P, that should be a lowercase p, is the probability of success. I'm just going to write it like this. Q is 1 minus p, the probability of failure. X is the number of successes. Okay. All right, so use the binomial probability formula. Even before we do this one, let's back up one more time to our example about the girls and the boys. That's something else from another class. Okay. So So if we're interested in the probability of getting exactly 2 girls, then it would be 3, choose 2. Probability of getting a girl, we believe, is what? 1/2, right? Yes? Okay, we're going to raise that to 2. Probability of not getting a girl is also 1/2. We raise that to 1. Okay, and so we get, somebody already verified that 3 choose 2 was 3, times 1/2 times 1/2 times 1/2, or 1/8, which gives us what? 3/8, which is exactly what we got when we listed out our tree diagram earlier. Okay, but instead of having to do that, now we're going to have a formula that brings us there. Okay, all right, so let's look at how we do that in this next example. I don't know which way to go. Let's see here. Use the binomial probability formula to find the probability of getting exactly 3 peas with green pods when 5 offspring peas are generated. Okay, so we already verified that this was a binomial experiment. That's what we would do first. Then we could think about the formula. We're interested in the probability of exactly 3 successes. This time we already said n was equal to 5, x is equal to 3. They told us the probability of a green pod was what? 0.75. Probability of yellow pod, which is the failure, is 0.25. If we were to write this out, we would do 5 choose 3 times our probability of success, which is 0.75, raised to the number of successes. How many successes do we have? 3. We're going to multiply it by the probability of failure, 0.25. That's raised to the number of failures, which is what? 2. Okay, so we could do that on our calculator. And so we get what? 5 choose 3. Okay, times 0.75 raised to the 3rd power. Okay, times 0.25 squared. And so we get 0.2637, we'll call it. Okay. Questions about that? Okay. All right. Okay.
I was about to ask what the answer was.
Okay. 0.2637. Righty. That's not so bad, is it? Okay, y'all a little quiet, but it's okay. All right. But yes, I can. I'm going to stop the video. Oh, I shouldn't have said that.